All right, expanding on our knowledge of vectors. So we covered some stuff previously, so now we're going to go into the dot product. So the dot product, so again, we think multiply. It's kind of like the same idea as multiplication, but we call it the dot product between them. And it is the sum of the products of the horizontal and vertical components, or the I and j components. So if v equals 7i minus 4j and w equals 2i minus j, find each of the following dot products. So first one we're looking for is the dot product between v and w. So remember, this is going to result in a scalar value because it's two products being added together. So that is going to be, let's go, v, w, handwriting's not doing very well. Product of the I component, so that would be 7 times 2 plus the product of the j components, -4 times -1. So 7 times 2 is 14, -4 times -1 is 4, 18. B is v with itself. What is v? So kind of like v squared. 7i minus 4j, so v dot product with itself. 7 times 7 plus, let's see, was it -4? Yes, -4 times itself. So we're going to get 49 plus 16. And then we do a little algebra, 49 and 16. Sometimes my addition's a little off. 65. And then that was it. All right. Properties of dot products. Make sure you read over those so you know it's similar to what we just went over: multiplication properties, distributive properties, what properties you're allowed to do with vectors and dot products. The alternative form of the dot product here, so sometimes is useful, especially if they're written in different forms. It's the magnitude of each vector individually times cosine of the angle for direction. All right, for the angle between vectors, so sometimes you're asked to find the angle between the two vectors, and that's just taking the equation that we looked at just a second ago and performing algebra to get theta by itself. All right, determining characteristics with vectors. So parallel, perpendicular. It's been a while, so just a quick reminder. Parallel are we've been over with lines. So as far as vectors are concerned, parallel vectors is when the angle between the vectors is either 0 or 180, because they're going the same direction. If the angle is 0, they're going to go the same direction. If the angle is 180, they're in opposite directions, but they're still parallel. They're just moving in opposite ways. They are orthogonal. Orthogonal is the fancy word for perpendicular, when that vector is 90 degrees. Another way to look at it is if their dot product is 0, that means they're orthogonal. I prefer the word perpendicular, but we got to stick with the vocabulary here. All right, example 2. Find the angle between the two vectors v equals 4i minus 3j and w equals I plus 2j round to the nearest tenth of a degree. All right, so we know that cosine of the angle is equal to the dot product between the two vectors divided by the product of the magnitude of the two vectors. So the angle theta is going to be the inverse cosine, it's not a very pretty S, but that's okay, of the dot product between the two vectors. They were v and w, yes, v and w over the magnitude, the product of the magnitude of the two vectors, v and w. So I'm going to go find the numerator and denominator off to the side rather than do this all in one giant mess. So the dot product of v and w, I'm going to find first. That is the product of the I components, 4 times 1, plus the product of the j components, -3 times 2. That is 4 plus or minus 6, so -2. For the magnitudes, I'm going to find the magnitudes individually. So the magnitude of, we'll go v first. Sum of the squares of each I and j component square rooted, so 4 squared plus negative 3 squared square rooted. That gives us 16 plus 9 under square root, which is 5. Square root of 25, which is 5. And then the magnitude of vector W is 1 squared plus 2 squared, sum square rooted. So 1 plus 4 under square root of 5. So this one we cannot simplify. All right. So getting everything plugged in. All right, so theta is going to be the inverse cosine of, the dot product was negative 2, over 5 for the magnitude of V times the square root of 5, the magnitude of W. So we go to our calculator, check your mode, where it says round to the nearest tenth of a degree. Make sure you are in degree mode or you will do this wrong. Second cosine, so we're doing inverse cosine of the ratio. So I'm going to get my fraction template. Negative 2 divided by 5 times the square root of 5. And we get 100.30. So theta is 100.3 degrees. So based on that angle, we know they are not parallel because we didn't get 180 or 0. We know they are not orthogonal because we did not get 90, nor was the dot product 0. Right, example 3, determine whether the given vectors are orthogonal. Sometimes it will say parallel or orthogonal or neither. So that's just comparing, did we get a degree, an angle of 0, 180, or 90, or somewhere in between. So like the last two are neither because we didn't get any of those answers. So we're essentially just going through the exact same thing we just did here. But because we're only asked about orthogonal, we technically only have to check the dot product. If the dot product is 0, by definition, they are orthogonal. So that would be a little bit quicker than having to go through the whole process of finding the angle. But if you forget that the dot product is 0 for orthogonal, just calculate the angle just like we did in the previous example. All right, so the dot product is going to be 2 times 6 plus 3 times negative 4, which is 12, plus a negative 12, which is 0. So it does say give a reason. So since the dot product of V times W equals 0, the vectors are orthogonal. That's a word. Orthogonal. Or perpendicular. All right, vector projection. So if we have two non-zero vectors, the vector projection of one onto the other is found by the dot product between the two vectors over the magnitude of the vector being projected onto squared times that vector. We also have vector components. So vector components lets us decompose one vector V into its original pieces, V1 and V2, where it's got parallel and orthogonal pieces. Okay, so the vector components, we're going to do one of these first. I probably should have put that example in between, but we'll be okay. All right, example 4, find the vector projection of V onto W. So make sure you know which one is onto which. So the projection of vector V onto W. So projection of vector V onto W, because I can't bold it, is the dot product between those two vectors divided by the magnitude of the vector we're projecting onto, W squared, times the vector W itself. So I'm going to go off to the side to find all this, and then I'll get it all plugged back in. So I need the dot product of V and W. So V2 times 1 plus the j's -5 times -1. That's going to give us 2 plus 5, 7. Then I need the magnitude of w, and then I'll square it later. So magnitude of w, I component squared, 1, plus j component squared, -1, square rooted, so 1 plus 1, square root of 2. All right, so we can go plug in. So the projection of v onto w is going to be the dot product, 7, divided by the magnitude of w squared, so square root of 2 squared, I'm not going to simplify just yet, times w, so it's kind of like a scalar times the vector w. The vector w was I minus j. So 7 over the square root of 2 squared is 7 over 2. Distributed, scalar distribution, 7 halves I minus 7 halves j. Now that we've done the projection, decompose v into two vectors, v1 and v2, where v1 is parallel to w and v2 is orthogonal to w. All right, so back up to this second one here. So decomposing it, it says v1 is equal to the projection of v onto w. Let's say that right. So the vector we just found, that is vector 1. So vector 1 is 7 halves I minus 7 halves j. V2, if we read back up here, V2 is the vector v minus v1. So I go get my vector v, 2i minus 5j. So v sub 2 is the vector v minus v1. So I go get vector v, I forgot it already, 2i minus 5j. Copy, paste, copy, paste, just need some parentheses. So remember, vector subtraction, it's similar to like combining like terms. The horizontal components go together, the vertical components go together. So we are going to subtract the horizontal components, 2 minus 7 halves I, and then we are going to subtract the vertical components. So that would be -5 minus -7 halves. Forgot it was negative. Oh, j, yes, j. All right, so 2 minus 7 halves, -3 halves. And then -5 minus negative turns to a positive, so -5 plus 7 halves, -3 halves, j. All right, last thing that we're bringing in with vectors is work. So work done by a force, we tend to call it W. Moving something from point A to point B is that resulting force F times the vector AB itself. So it's a lot easier to think about this in the alternative form. We don't really deal with it in the vector format. We like the positional format. So the work done can be represented as the magnitude of the force times the magnitude at which that force is applied, so the length at which the force is applied, times the angle between that force and the direction of motion. Work is measured in weird units because we wind up taking a force that's applied in pounds on a directional vector, like length, so pounds feet or pounds miles. Newtons, we probably won't be measuring in newtons. We're going to stick with units you're familiar with. All right, example 5, it says a child pulls a wagon along level ground by exerting a force of 20 pounds on a handle that makes an angle of 30 degrees with the horizontal. How much work is done pulling the wagon 150 feet? So, if we think about it, just to kind of give you an idea of what's happening, here is the horizontal. So it's like the handle of the wagon is like coming up like this, and the handle of the wagon is making this 30-degree angle with the horizontal. The force of 20, the child is pulling the wagon, so that means he's moving this way, or she, it doesn't say, and he's applying 20 pounds of force. And he's moving this way for, I believe it said 150 feet. So the work being done is equal to the magnitude of the force being applied, which is 20 pounds, times the magnitude at which it's being applied. We don't need the units here. So 20 pounds times the distance at which he's applying that force, which says 150 feet, times cosine of the angle it's being applied. So we could do this one and give an exact answer, but usually this is something we will do in decimal form. So make sure you, again, degree mode, 20 times 150 times cosine of a 30-degree angle gives us work of 2,598 point, let's see. It doesn't say, so let's go with to the nearest whole number. So that would be 2,598. And the units are the units of the magnitudes. So that would be 20 pounds and 150 feet. So feet, pounds, foot, pounds, I don't know, pounds, feet. However it is you would like to write it. You're not going to have to type the units in. So again, same thing here. Be very careful with that mode on your calculator. Always double check it before you type something in.